This video is going to be an introduction of Chapter 4. Just a forewarning, this is the chapter that most students struggle with in the first quarter. It's the one that most students will tank. So make sure that you stay on top of your studying, make sure you focus on the concepts in the chapter, and when you don't understand something, make sure you seek help, okay? First, we got to talk about solutions because this chapter has a lot of solution chemistry in it. So there's a term called aqueous solutions. Aqueous means dissolved in water. Water then is going to act as the solvent in all aqueous solutions. So the solvent is the one that is doing the dissolving of the solute. So basically water is dissolving whatever has been put into the water. The solute is the stuff that was dissolved, and the solution, which is this whole chapter, is about the combination of the solute and the solvent. So it's both the water and what was put into the water will produce a solution. So in Kool-Aid, what would you say is the solute? What has been dissolved? Now most of you know it's either the powder or the sugar. What was the solvent? Well, you use water to do the dissolving. And the solution? That's a combination of the water and the powder, which is what we call Kool-Aid. So Kool-Aid is a solution. Now, water has a specific structure. First off, you know it's made up of two H's and an oxygen. Its shape is bent. It also has a bond angle of about 105 degrees. Both of these bonds are what we call polar covalent. Now remember, covalent means that the oxygens and hydrogens are sharing electrons in the bonds, but because they aren't sharing them equally, it's a polar bond. And the reason they're not sharing them equally is because the oxygen is more electronegative than the hydrogen. The oxygen is pulling the electrons towards itself. And when it pulls the electrons towards itself, there is a partial negative charge, which is represented in the blue, on the oxygen, and a partial positive charge on the hydrogens because they are more electron deficient. Now, we call that a dipole. You have two different poles, a negative pole and a positive pole. So, since water is a polar molecule, it has a positive and negative end to it, positive end being the hydrogens, the negative end being the oxygen. That's very similar to ionic compounds, because in ionic compounds you have a cation, which is positive, and an anion, which is negative. Also, you need to know that ionic compounds are also called salts. Okay, it's just another term that is synonymous for an ionic compound. So what is hydration then, other than drinking water to quench your thirst? Okay, in chemistry, hydration is the description of the process of water molecules surrounding a salt, which is an ionic compound, and causing it to fall apart or to dissolve in the water. There are some strong forces that are present because both the ionic compound and the water have positive and negative ends, and so those positive and negative charges are attracted to each other, and the water is able to rip apart the salt and cause it to dissolve. I'm going to show you a video on how this works. Okay. The water molecules are coming in and grabbing each of the ions off of the salt. If you notice, the hydrogen end is very positively charged. The hydrogen then is going to surround itself on the negative ions, which if you look here, okay, and you look closely, you'll notice that all of the hydrogens are surrounding what looks to be like the green ions in the salt. So if the hydrogens are attracted to the green ion, then that ion must be negative. Conversely, if you look at the waters in the bottom corners that have surrounded the salt, all the oxygen or red ends of the water are surrounding the other ion, the gray ion. That means that gray ion must be positive because those oxygens are negatively charged. So I'm going to show you once again what's going on, but if you notice, those ions are surrounded on all sides by water molecules, which is what we call hydration. So see, once more you can see they come around and then they rip it right off of the salt. Okay. Now, moving on. When hydration happens, positive ends of the water will align, which are the hydrogen side, align with the negative ions of the salt, and the negative ends of the water, which is the oxygen end, align with the positive ions of the salt. And there's a close-up view of what is going on for you. This is just another view so you can see in the left all the oxygens are facing the positive ion, and in the right all the hydrogens are facing the negative ion. Now, after hydration is complete, all of those salts have been ripped apart and are now dissolved in water. So when you look at the equations on the left, these are both salts. They're both ionic compounds. Ammonium nitrate starts off as a solid, and after it's undergone hydration, the ammonium and the nitrate are now separated, but yet their states of matter are now listed as aqueous because they've been dissolved in water. The same thing is true of the lithium carbonate. It starts off as a solid, and when it breaks up, it makes two Li plus ions, because in lithium carbonate there are two lithiums per every compound, and one carbonate ion. And notice they are listed as aqueous because they've been dissolved in the water. Now, solubility is a term that describes the amount of a substance that dissolves in a given amount of solvent. So in our case, it would be how much salt can you dissolve in a given amount of water. Now, the solubility can vary. It depends on the relative attractions those ions have for each other, because the more attracted they are to each other in the salt, the harder they are to break apart. And it depends on the attractions those ions have for the water. The more attracted they are to the water, the easier it is to break it apart. So it's a competition between how attracted they are to one another and how attracted they are to each other. Okay, so what I'm saying is how attracted the ionic compound is to itself, and then yet how attracted that ionic compound is to the water. We'll talk more about solubility when we get to chapter 16, which is one of the last chapters that we cover in this class. Now, the last topic you really need to know is the difference between strong and weak and non-electrolytes. An electrolyte does not just apply to Gatorade, okay? An electrolyte is the term that means the ability to conduct electricity. There are strong, weak, and non-electrolytes. Strong electrolytes can conduct current efficiently. Weak can only conduct a small amount of current, and non do not conduct any current. Here's a picture of a strong, a weak, and a non-electrolyte. And the difference, what makes them strong, weak, and non, is the number of ions they make when they've been hydrated or broken apart. If you look at the left picture, there are a lot of positive and negative ions. That's the sign of a strong electrolyte. In the middle picture, only one of the 6 molecules has broken apart. That would constitute a weak electrolyte. And in the yellow picture, as you notice, there are no ions, which means it's a non-electrolyte. Here's what the consequences are of being a strong, a weak, and a non-electrolyte. In the beaker in the bottom, there is a liquid that has had a salt dissolved in water. That liquid has these ions floating around. The more they dissolve and break into their ionic state, like in the left picture, the more current you get, so the light bulb is very bright. In the middle one, it didn't break apart as much, like you saw in the middle picture before. There's only a couple ions in that liquid that you see. Therefore, you only get a weak light. And in the right one, none of them broke apart, so you have a non-electrolyte. So you need to know what categorizes them as strong, weak, or non-electrolytes. You have to be able to look at a compound and go, oh, that's a strong electrolyte, or ooh, that's a weak electrolyte. There are 3 classes that fall into the strong electrolyte category. All salts or ionic compounds are classified as strong electrolytes. Strong acids, there are 6 of them. You must memorize these 6 acids: HBr, HI, HCl, H2SO4, HClO4, and HNO3. You need to be able to memorize them, and I expect you to have them memorized by Monday. There are also 9 strong bases. Use your periodic table, folks, and you'll notice a trend amongst them. Lithium, sodium, potassium, rubidium, and cesium are all in group 1, and if you notice, they're all bonded with hydroxide. In group 2, you've got magnesium, calcium, strontium, and barium, and they're all bonded with hydroxide, but they're bonded with 2 hydroxides because they're from group 2 and they have a charge of 2+. Look on a periodic table and sketch them out. You could even draw a big bold line around them so that you know which 9 are considered strong bases. Weak electrolytes are described as anything that's a weak acid. Well, how are you going to know if it's weak? You're going to know it's weak if it wasn't strong, but it began with an H, okay? Like HF, for example, is an acid, but it's not on the list of strongs, so it's a weak acid. Also, if it has what we call the Cu group, which is a COOH, If you notice that group in the compound, then it's also a weak electrolyte. That is a carboxylic acid group, and that is considered a weak electrolyte. Weak bases would be anything that's with a hydroxide that's not on the list of 9 bases that I just previously listed. And if it has an NH2 group on the end, it's also a weak base. Or ammonia. Ammonia is also a weak base, NH3. Lastly, anything that's polar covalent can also be classified as a weak electrolyte, like water. Non-electrolytes would be classified as non-polar covalent compounds, so those things that are sharing electrons equally, such as methane, or a compound that starts with a carbon and ends with just an OH group, which are called alcohols. It's not a COOH group, like I just showed you, it's just a mere OH group. But remember, if it starts with a metal and ends with an OH, it could be a base. These groups start with a carbon and end with an OH. Okay, and I gave you an example there. For example, lithium hydroxide is a strong base and a strong electrolyte, but CH3OH is an alcohol and is a non-electrolyte. So just to practice, and then we'll be done. When you see a compound, you have to go, okay, what is that? Okay, HCl, it's definitely an acid. Is it a strong acid? Well, I have to memorize them, and it is. It's a strong acid. If it's a strong acid, then it's automatically classified as a strong electrolyte. HF, also an acid. Is it a strong acid? Well, I check my list of 6, and it's not. Once I know it's a weak acid, I also know it's a weak electrolyte. C2H5OH. I notice this OH group, and I notice it doesn't start with a metal. That means this is an alcohol. If it's an alcohol, then it's a non-electrolyte. It will not conduct electricity. In the next one, I see this Cu group. A Cu group is the signifier of a weak acid. Once I know it's a weak acid, I know it's a weak electrolyte. Ooh, in the next one, I see an OH group. It's an OH, but this time it's starting with a K. That means it could be a base, and I need to check my list to see if it's a strong base or a weak base. Once I consult the list of strong bases, I will see that KOH is a strong base, therefore it is a strong electrolyte. The last one, it's not an acid, I don't see an OH, I don't see a Cu group, so what is that? Well, magnesium is a metal and fluorine is a nonmetal. It's an ionic compound which we call salts, and a salt is classified as a strong electrolyte. Make sure you know how to classify compounds when you see them as strong, weak, or non-electrolytes. If I give you a list on Monday, you better be able to classify them as strong, weak, or non, and also give me the definitions of what it means to be an electrolyte and also how hydration occurs. I'll see you on Monday. Have a great weekend.